is a professor at the University of Washington and also at MSR. And as you probably know, Sham has had lots of work behind a lot of things in machine learning, from policy iteration linear bandits to even latent variable models. And I'm really excited to hear from Sham today. Sham, are you around? Oh, great.
All right, we can see my screen
Yep.
and my voice. Okay, sweet. So again, thanks to the both the long-term organizers of the RL workshop and the organizers for this week, because it's just like it's super stimulating and it's a great time to have this. And of course, always giving a big thanks to Peter Bartlett, because it is just a ton of work for him. So I'm excited to speak about some recent work with Rusong and Dean on offline reinforcement learning. So this is a good bridge to the next workshop, actually, because that's entirely on offline reinforcement learning. Rusong actually is in the chat, so if you have questions, feel free to either ask him or just go ahead and interrupt me and ask. Okay, so we can see it advancing. Just okay, great. So so what is offline reinforcement learning? It's basically the approach is to try to utilize offline or observational data to try to help in learning basically causal sequential decision-making strategies. It's becoming increasingly important now, particularly in a number of like high-stake applications, just going beyond games and things like that. We do have a lot of data, and in many settings, it's actually pretty hard to run causal experiments, and we'd like to really leverage this offline data. Okay, so what are the challenges here? So let's consider this healthcare example as a running example, because I think it's a little more compelling. So what are the challenges in this space? Well, we've got a sequential decision-making problem because the decisions affect the future. As I said, we can't, in many of these settings, we can't run causal experiments very easily, or because we just have the data offline, and a real concern might be just not enough data in various subgroups. And on top of that, we've got this curse of dimensionality, where effectively we have an infinite possible set of configurations for the type of people that come in, and we need to use some kind of function approximation to handle this issue. Okay, so let's just start simple and get some intuition so we're all on the same page of when we agree offline learning is okay. Okay, so this would be easy, but it's definitely helpful to just be very concrete, see when things are fine. In fact, let's make life even simpler. Forget about the sequential decision-making aspect of things in that how our decisions affect the future. Let's just consider the Horizon 1 problem, which is like a bandit setting. And it's still sequential in that we might be changing our behavior, but the world itself, there's no sequential aspects to the world. There's no state. Okay, so consider a setting where notation is going to be S is the state. It could be all kinds of patient characteristics. So there's effectively an infinite number of possible states. We have an action space. It could be large, could be small. And we have a reward function, which is some measure of the quality of the outcome, like how long it takes the patient to get better, or some measure of how well they're feeling. For this setting, let's just go ahead and think about one of the most commonly used approaches, which is we model the outcome as a linear function of some feature vector of S and A. So phi is some d-dimensional feature mapping. And when does this work? Okay, so again, there's no sequential decision making. So when does this work? So when does the offline learning work here? So we're gonna have a data set of endpoints of states, treatments, rewards. Define sigma to be our feature covariance matrix. It's like a D by D matrix. So let's make two assumptions here. First is realizability. So let's actually suppose the linear model is correct. Okay, not just where our algorithms using these features. Let's actually suppose the linear model is correct. And let's suppose we have this coverage property, because if we're going to do well, we had better see kind of all directions of the data, all directions of our features, and this coverage assumption is literally a minimal eigenvalue assumption on this covariance matrix. Okay, so if that's bounded away from 0, we've effectively seen all the directions in our data. Okay, and under these two assumptions, it's pretty straightforward to convince yourself that provided we have, some amount of data that scales with d over epsilon squared divided by lambda min, what's nice about this is we'll be accurate on any new test point. That's what this realizability lets us do. Not just on the distribution for which our data is collected, we'll be good on any test point. Okay, and this lambda min is really coming from a shift factor that we train on one distribution and we're tested on another. Okay, so again, this is just a straight up regression, but we're heavily leveraging this realizability assumption. And note these are very strong assumptions from the practical side, because in a high stakes application, we would never believe these. Like, we definitely are very concerned about model misspecification and all kinds of sampling biases. So this is very much an abstraction in this setting. But if we have it, it's easy. So now let's jump to the sequential decision-making setting in a very small state example. So consider 3 states in this toy MDP. Just set up some notation, and then we'll set up the problem. So super simple problem, a small number of states. There's a user notation. We have transitions, we have rewards, say, that are bounded, and we're going to get an offline data set of endpoints, except now the offline data set is a state action where we transition to and the reward. Okay, so it's quadruple. So it's the triple of SAS prime with the reward. Again, our goal, let's make life easy. Let's forget about even policy improvement. Let's just say, can we evaluate how good a single policy is, like a known policy is, from the start state? Okay, so we aren't caring about improvement at all. We just want to evaluate a fixed policy. Okay, and one standard approach is just do this backward induction, this fitted Q iteration. So take your offline data set, and we want to estimate the value of this policy pi, and we just move backwards with the usual notation. So Q hat, we just set it to be the empirical reward, and then you do these Bellman-based backups. Okay, so we're all familiar with this. And when does this work? Well, we know this is going to work if our data set has a reasonable number of samples at every state action pair. Okay, so this is just coverage, because it's a small problem. If we see every state action in our data set, we'll be able to estimate the value of the policy accurately. Okay, so for this one, we need coverage. And of course, this world is easy because the number of state actions are small. Okay, so now let's go back to, say, this problem and what we care about doing. Okay, so what we're going to try to do, which is what we do in practice, is just kind of merge these two ideas, where we're going to try to do some fit in this backup procedure. And our hope is we're going to try to avoid this 2 to the h sample size, because if we just tried this naive thing on this tree, we're really going to have to see 2 to the h samples before we can do anything interesting, because that's kind of the cases we might go to. Okay, so we're trying to get some kind of guarantee that doesn't depend on like the number of configurations. And the hope is, we've got these features. We're going to think of a setting where we have some features. These features will hopefully help us handle the curse of dimensionality, just like for regression. And just like regression, we're going to think about extending this coverage assumption, where we think about our future covariance matrices are going to somehow be well conditioned at every level. Okay, we'll make this precise. Why does this seem reasonable? Well, if we have the same assumptions I showed you at the last level, regression would be fine. And from regression, we know we're going to be accurate at every possible last stage configuration. Right? That was the whole point. At every possible configuration, regression's good. And we might hope we can use that to plug that into the previous stage and just do regression again. Okay, so that's one candidate algorithm. But more generally, we might just care about information theoretically. What are the limits? Like, our question really is, what are the information theoretic limits of handling data reuse with function approximation? So not just this kind of backup-based algorithm, what is achievable, and in particular, what assumptions make certain classes of, what assumptions will make this problem, what assumptions will allow for sample efficient estimation of the value of a policy. Okay, so specifically the talk will try to understand what are necessary kind of representational and distributional conditions which will permit sample efficient RL. Okay, and make life easy, we'll just focus on policy evaluation. So we're not going to worry about improvement. We just want to take our offline data set, figure out how well we can accurately estimate the value of a fixed policy. Okay, and the main result for the lower bound is going to be showing that the analogs of this realizability assumption and coverage assumption are definitely not enough for sample efficient offline learning. This is a super basic question, and we'll try to give some intuition for why that's the case. So this is pretty depressing at some level. And from the upper bounds, I'll discuss some prior work here where it's really showing we need much stronger assumptions for this to occur. And I'll also discuss, time permitting, this question of like, how generic is this issue of amplification? Like, you know, like, sure, we construct some lower bound showing it's going to happen. Do we really expect to see these effects in practice? And I think this is one of the real questions we're thinking about now, which is particularly relevant in various high-stake applications. Okay, so let's just lay out the setting where we're working with a linear value function approximation. As actually I pointed out, there's been a ton of work on this in RL in the last few, well, actually from quite some time ago, but in terms of the theory, there's been a revival looking at this. And this is really arguably the simplest case. And to attack this problem, it's just the natural extension of regression. Okay, so the setting is going to be, we have some data collection distribution, mu1 and mu-h, and at each stage, this is giving us these triples of an SA S prime, where the semantics are S prime is drawn from the underlying distribution, reward is, and the rewards are drawn from the correct distribution. And we're going to get some IID data set from these distributions. Okay, and our goal is, let's just evaluate a single policy. We know the policy, we'd like to estimate its value. So that's our goal. Okay, so no improvement here, just policy evaluation. Okay, so we're going to make these two assumptions precise and then see what we can get. Okay, so assumption one is going to be a bit stronger assumption than realizability in that, okay, so we assume we have a feature mapping, and the case we want in practice is the dimension of this mapping is smaller than the number of states and actions. We're going to assume that every policy, so fix the policy, or take any policy you want, and there's going to exist a weight vector such that the Q function is linear in this weight vector. Okay, so this is for every SA pair in the MDP, the Q function is linear. Okay, so this is for every policy we have a linear state action value. Okay, so not just the one we're interested in. So it is a reasonably strong constraint. Okay, so sometimes people refer to this as linear value function approximation, but it's realizable. Okay, so the second assumption is, we kind of know what needs to happen at h equals 1, which is regression, which is we need coverage. So just assume your features are bounded less than 1. That's without loss of generality. And let's go ahead and assume the best possible coverage in a spectral sense. So with respect to our data distribution, mu, we're going to assume that our feature covariance matrix is 1 over d times the identity. Okay, and that is the best possible coverage because this is the largest minimal eigenvalue you can have when your features are bounded by 1. Okay, so this is kind of the best shaped covariance matrix for covering all the directions. So we're going to go ahead and assume that. Okay, so we can't really, at least in a spectral sense, we can't hope for anything stronger. Okay, so are we good up to here? So it's just, all policies linear, we have coverage. From what we said before, h equals 1 is completely fine, okay, because this is what we need for regression to work. Okay, so, right, so we set, so we set things up in that, we've got our two nice assumptions. We've got realizability now. That's the hope is that's going to handle the cursive dimensionality, and we've got feature coverage. So we're kind of not missing these missing cases in some aggregate sense, because obviously we're missing cases, but we're not missing directions because this phi has aggregated these cases. Again, our question now is, this is more of intuition from an upper bound perspective, but are these assumptions somehow enough to allow us to move backwards? Now, more generally, we're interested in an information theoretic lower bound here. But when you see this, the obvious thing to think about is, can I just go backwards? Because regression is going to work. It's going to be accurate everywhere. Can I plug this into one previous step and keep moving backward? And will this give me a good estimate of the value? So, I think those of us studied RL, we always try things like this, and we want to know, will this work? Okay, so before we get to the main result, let's look at what's known here, because this has clearly been studied in various different incarnations. So probably the largest amount of work in this setting was with regards to importance sampling. Okay, and here, we kind of know that naively you need exponential and H samples and this broader set of offline RL using importance sampling. It's kind of hard to put function approximation in this framework. But that said, importance sampling it's pretty honest and it works quite well in practice, but it's pretty hard to get past this XH barrier with it. Because it's specifically on this setting of using linear value function approximation, we know if we have stronger constraints on the system, we can do this. So we have this sort of policy completeness, or sometimes this is called policy closure is better. I've seen it referred to as a completeness too. I don't know why I use that one rather than closure. But basically, this assumption says that if we can back up every possible weight vector, so take a weight vector, can we back it up? Then we can actually do offline RL. Okay, so and this is a stronger assumption in the sense that if we assume a policy completeness for a given policy, that implies realizability for the policy. And if we assume we can do this for all policies, like all policies are complete, that implies realizability for all policies, which is our assumption A1. So this is definitely a much stronger assumption. And if you think about it, you can really see precisely why this really has, it really says something about the way the features interact with the dynamics. Okay, and recently, there's a bunch of work here. Chabo is one of the earlier authors in a more general setting, but specifically for the case of policy evaluation with completeness, there's a recent paper by Duan and Mengdi showing minimax rates here with a stronger condition. And if you don't have this condition, there's a recent paper by Nan and Ji showing that with stronger density ratio lower bounds, you can do it. But all of these are significantly stronger conditions to say anything here. Okay? And the question is like, look, what is possible here? Because these other conditions are substantially stronger than regression. So the main result for the lower bound is you can't do this. So take any offline RL algorithm. So this algorithm is going to take a policy as input. So it knows the policy, it knows the feature mapping, and it's given a data set. So it knows this like gigantic table of feature mapping. We don't care about computation. Okay, and the point now is like if you have coverage, there's going to exist an MDP that's also realizable, such that for any policy, A is going to require d to the h/2 samples to estimate the value of this policy. Okay, so basically you've got realizability and coverage, and you can't estimate the value of any of the policies in the MDP. Not just one, just you're given some policy, we can't estimate the value of any of them. Okay, so every policy here has a linear value. Information theoretically, we can't estimate a single one of them. Okay, so that's the main lower bound. I have time here. Okay, so let's make some comments about this and interpret things, because I think this has a number of interesting implications. So, so let's make some observations. So I believe this is the statement clear. Basically, you're just doomed here under these assumptions in a pretty strong sense. Okay, so so let's just jump to some observations.
Can I ask a quick question, Sham?
Yeah.
So, you often in this setting, I guess you're simulating a particular policy, so you can at least estimate that one.
Yeah.
Do you think it was important here that you're not
No, it isn't. Like, so we have some comments in the paper. This, yeah, like in this case, you can definitely get the value if you have your trajectories of that one, but most of them you still can't get. So we have this comment in the paper. The fact that we haven't kind of given the data set from one policy as trajectories, it doesn't make a difference. It's more to emphasize how severe this problem is, but we directly handle this other one, and morally, like most of them, you're still burned on.
Hey, Sham, I have a related question with Dan. What's the significance of like impossibility to do this for like all policies, right? Because if I think of it naively, like if I copy my action for each state, if I copy my actions like multiple times, then if I can't do anything with any one policy, like all the policies are the same thing. So I cannot evaluate anything, right?
Come back to that one later. So the significance of that short is that for lower bounds, we want to put more constraints on the system. So constraining the problem to be linear in all policies is a much stronger constraint on the system than one of them. That's the truth. So I can come back to that later.
Yep.
So let me just proceed because I want to share some experiments too. Okay, so a couple of quick comments. There's clearly a separation between RL and supervised learning in this offline setting because like regression is fine here at h equals 1. Okay, a pretty puzzling thing here is this. So I'm going to call this algorithm of doing backups plus regression, least squares policy evaluation, LSPE. So this is doing regression, plugging things in. So this is surprising because you get an unbiased estimator here. Like this is when we started doing experiments. Like if you think about this, regression's unbiased, you actually get an unbiased estimator here. It just happens it'll have exponential variance. Okay, and what's interesting about this lower bound construction, it's super simple. It's an MDP with only DH states and 2 actions. So the online problem is trivial to solve. Like it's not like some gigantic MDP like some of these other lower bounds that we have. It's a very small MDP. It's a little bigger than the number of states, but like trivially. Okay, and those of us working in this, we always see this geometric error amplification even under realizability in our analysis. And in practice, we see it too. And I'm not going to discuss the construction too much, but I definitely recommend people to look at the paper just because, okay, let me put it this way. Like, I wished I had read this construction years ago because like we keep doing analysis and every time we keep seeing this amplification. And even if you don't care about like this offline problem, it's helpful to see concretely how this amplification can occur for a given algorithm because this comes up so often in analysis and it's a very simple like gadget to be used in like other lower bounds or upper bounds and coming up with cases where things go wrong. So it's actually a very simple construction, which I think really highlights how bad things are. Okay, so I do have a couple of minutes left, and I think I started a couple of minutes later. So let me just make a few comments about upper bounds and how worst case this is. Like, how generic is this error amplification? Say, we gave this lower bound for information theoretically, but for upper bounds, like what's going to happen if we did Bellman backups plus regression, okay, on real problems? Like, how pathological is this? So we know it can occur. But on the other hand, like, look, if it's tabular, or if you consider a case where the number of states is the dimension, this will not occur. So some cases it absolutely does not occur, like because regression plus backups in the tabular case, there will be no amplification. Okay, so in a sense, like what cases is this actually occurring for? Okay, and before we even actually did anything like formally figured out this lower bound, we just tried it, and this was either like the second or the first thing we tried. We just had massive error amplification. So the x-axis is the level. It's kind of going backwards. So at level 100, that's the last level. And we're plotting here the L2 error in estimating the weights with this backup algorithm. And I'll go through the example a little more precisely, but you see like, it's not a log plot here. It starts like 10 to the minus 6. Everything's bounded between 0 and 1. It blows up to 10 to the 30. And this was like literally just some construction we cooked up when Wusang was trying it out. Like all of us independently, like, wait a minute, this algorithm is unbiased. What's actually going to happen? And then the second thing we tried was like just explosion. Okay, so so specifically, let's look at this least squares policy evaluation, which is use Bellman backups with plugin estimates. let's so here's a very helpful way to think about things with inequality. So we've got n data points. Define phi to be your feature matrix, which is of size n by d. So just concatenate all your data into your feature matrix. Define phi bar to be your next state feature matrix, which is where you go to from SA. Okay, and let epsilon be the noise in the reward vector. So the reward you observe is the true reward plus a little noise. Okay, why this is nice, why we want to look at phi bar is suppose w hat h is what our weight vector is at level h. Okay, so the prediction of the values is phi bar w hat h, because if you think about it, if we're at h minus 1, we're going to be plugging in some target when we do a regression. So at h minus 1, that goes to level h, and we're doing a regression, we're using what comes in to back up at h minus 1. Okay, and what's are we going to use for estimate? We're going to use where we go to times our estimated weight. So phi bar h times w hat h is like the regression targets we're plugging in this algorithm, because at h minus 1, we're going to take our basis, try to regress where we go to at the next level. Okay, and the main point I want to make here is because you're just doing these regressions, you can just, with an exact equality, unravel what the estimator looks like. And you see it's like a product of a bunch of matrices. So if you can see my cursor, this is like the XX transpose, this is X. So forget about everything past here. If this was Y, this would be regression. This is XX transpose, this would be XY. Okay, but Y is the thing coming from the next level. So you plug that in and you kind of keep unraveling this object and you get this equality. And what's nice about this is like, look, equalities are great. So, and I'm assuming that we have a deterministic MDP and all the noise is coming from the reward, right? So this means like, we know exactly how this algorithm is going to behave because we can fix these matrices for the deterministic MDP case. We can see what happens. Okay, and it literally just boils down to some non-expansive property of this product of matrices. And now the issue is you just massage them. So we give, in the paper, a sharper condition for when it doesn't explode in terms of distribution shift. It's sharper than what NAN has, but that's only because we're doing policy evaluation. Okay, and this paper by Duan shows that completeness works, and you can also show it's non-expansive. Let me take like 2 more minutes, and I'll just show you some quick experiments. But at the end of the day, you have inequality. Now you can start trying things. So we can simulate an MDP. We just cooked up like a simple chain MDP that the states just don't interact, they just fall all the way down. It's a sparse MDP. We make it complete for a policy by just taking the true Q value and add extra features. So it definitely contains the feature vector of the correct one. This dashed block is, we take the first 2D guys to be the basis that the algorithm sees. So we've got coverage, we've got realizability for this policy. And it's deterministic. We put a super tiny amount of noise of 10 to the minus 10. Okay, and we say, do we get amplification? Okay, so we tried this. No. Okay, so the same plot. You do level by rewards. It's like 10 to the minus 10. You see no amplification. You could look at that Frobenius norm of that mess of products of matrix, no amplification. Okay, but let's modify this a bit. And instead, we're going to make our basis to be rather than D of them, we're going to say our data set is coming from, rather than 2D, a data set's going to come from a smaller set of points. Okay, but it's still basically well-conditioned, a small amount of noise. I can take you through this in questions later if you're interested in this, but it's just a modification of the previous example where we choose a smaller number of points in our offline data set, but it's still like very well-conditioned, a super tiny amount of noise. Do the same experiment again, massive amplification. Okay, and the product, so this is again H by our error, this is H, and this is the Frobenius norm of this product, and it explodes. And it's very easy to get examples like this. So the main point, like I'm making here, let me just wrap things up, is that you can look at the talk for these examples or email us, but like, look, this offline problem, it's information theoretically. We can't do it with coverage and realizability alone. We definitely need stronger conditions. I think it's worth pointing out why this is important in that for like these important applications, we really do need to take a fair bit of care because look, even in the short horizon problem, it's already hard due to model misspecification and sampling biases because like our modeling assumptions aren't correct. And we really care a lot about this because, you know, if you're doing treatments and things like that. Okay, and when we move to H equal bigger than 1, the sequential decision-making setting, the situation is substantially worse because under the same set of assumptions, in the best case scenario, it might not even work without stronger assumptions. Okay, and that's pretty concerning. Okay, and I think when you start playing around with it, it's very easy to get error amplification in some cases. Like without these stronger assumptions, if you start toying around with it, you really will see error amplification. And more importantly, this equality, like it's an equality, it's very helpful. It's equality for an algorithm, but what's becoming clear when we try it out is that our upper bounds are also quite loose too, that a better check is looking at you know, the way these matrices behave, because there's other cases where we don't see it and other cases where we do. And we really need to kind of look more carefully about the actual behavior of regression to see what's going on. But I think there's a strong reason to believe that to get this to work, we really do need like better features. And if we just do the usual machine learning thing, kind of cook up some feature set, we think it's okay, I think we're going to see amplification. And this is joint with work with Dean Foster, who's a good friend of mine, a statistician, and Rusang Wang, who's been doing awesome work. We were just doing a bunch of work together in this broader context of trying to understand what are the conditions we need, what are the kind of representational conditions we need for effective reinforcement learning more generally. And yeah, like Rusang's just been doing great work in this space. So thank you very much, and I'm happy to take some more questions.
Thank you, Sean. It's a great talk. Really kind of surprising. Do you have an intuition for any sufficient conditions where, you know, amplification will not happen?
Yeah, so in a sense, like these are the two I mentioned from like others, that sufficient conditions are this sort of a low distribution shift. And what that means is that the product of this, basically phi bar has to look a bit like phi in a spectral sense. There's a more precise version of that, but that's one. And another is this policy completeness, that for kind of every weight vector, somehow it has a certain projection property. You can write it in terms of the matrices, but there's a certain projection property that the infinity norm basically doesn't expand. Okay, it's like, you know, they write it differently, but you can verify that the completeness condition, which is saying that, you know, every Q value lives at, you know, every possible w dot phi, when you back it up, lives in the space of phi, then that works too. So these are sufficient conditions. But the main point I want to mention is because of this equality, these sufficient conditions don't really capture what's going on, because we've definitely can come up with cases like we've just been, you know, doing random features to kind of cook up this problem, but forcing realizability. So you can always start with a true Q vector and add features, because then you'll always have realizability. And we can definitely see cases where these cases aren't sharp. And I think the moral of the story here is that, you know, in a real high stake application, this product of matrices, it's kind of like an importance sampling ratio, but in feature space. Like you could actually just literally, rather than doing importance sampling, you could literally just compute this spectral amplification. And if it's occurring, you know you're burned, right? So rather than kind of doing importance sampling, this seems like a much better way to kind of control which policies you can accurately estimate, because this is an honest equality.
Can I suggest something different? Hey, Sham. So I think this is a great talk, and I like the work a lot. And as I already discussed a lot with Russell and you. So I think, so since you're talking about policy evaluation in the offline case, I want to contrast this with some of the like possible results, not the one that you mentioned, you know, for policy optimization that you cited, but you actually cited the other paper, of a recent paper for policy evaluation. And I think to in a practical sense, policy evaluation with realizable QPi is actually, I would say, practically feasible. And I think to contrast with the result you have here and all the great intuition you're building up, I think there are two things. A, maybe we're aiming at the wrong goal of accurately estimating the precise performance. Two, maybe we're using the wrong algorithm that we're doing this backup. So it turns out that, a lot of us recently, so first of all, in terms of algorithm, a lot of us recently are looking at these algorithms that does moment matching.
No, but hold on a second. This is information theoretic. So you need
yes, I know. Yes. So that's my second point. So the positive result we get is that instead of we can estimate the point estimate, we give you an interval that could be loose, but sometimes it's tight. But when it's loose, you do see it. So this is in the sense like similar to what you're saying here, like as checking phi times phi bar. It's like when you fail, you failed.
Yeah, no, so that's right. So you can just look at these matrices, but that's not saying that it works. This is the same, like importance sampling doesn't work. You just get valid intervals.
Right. But my point is that I think I'm recently more and more convinced that for all policy evaluation, I would never use these backup methods. What I would do instead is do these like moment matching methods that check the, essentially you want to optimize the current value and the future value like together. You never want to fix future value and then optimize the next value.
Look,
no, you're not.
You're gonna have the like amplification effects because I can look at the moments and I can get exactly the same kind of issue because what's gonna happen when you match moments is your intervals there are going to be getting pushed through these amplification matrices, and you literally can see this if you think of the moment matching thing, because you're going to say some phi.w is like matched to something, that w is getting pushed through some matrix, that next one is pushed through some matrix, and that's exactly this this product that comes up in a slightly modified sense. And the issue still is some cases you're okay, but those cases you actually, they're much stronger conditions when this occurs. Now, I think the point that we, under realizability will have confidence bounds. I think this is a very good point because in practice, like that means there is something better to do here than importance sampling, and I think that's actually quite valuable because now you could try to, at least compare things in some interval, but that interval. Is like my claim again, this is more intuition playing on these experiments. My feeling is that interval is only going to be reasonable if we have better features, like and getting those better features is not at all obvious how that's going to happen. Like actually I talked about some of those things, but those features really have properties about how those features get pushed through your dynamics matrix. Because that's exactly
so I think, Sham, I think maybe what I'm talking about, the methods I'm talking about still slightly different from the moment matching thing you're talking about. So basically what we have is like, if you have Q pi in Q, that's the only condition you have, you always have a valid interval. But as you said, like sometimes maybe this interval is just too loose to be any meaningful at all.
Yeah.
But under some conditions, some of the sufficient conditions you mentioned, like these intervals will be sufficiently small. But yeah. I think the point, which is similar to your idea of checking phi times phi bar here, is that it's still nice enough that, at least when we fail, we know we failed. So, yeah.
So that.
Can I ask, so what was second question here for me, sorry, but so I think I get the intuition for why this works for why LSPE has this exploding variance. But is there sort of a similar intuition for why this is inherent to any algorithm?
Yeah.
How does that construction work?
Yeah, so this is why I wish I had a little more time to show this, because I feel like this construction is just helpful. It was kind of the gadget that Chaba uses too in their linear Q star paper, but it's because it's information theoretic, and when we do this, we see the amplification. Basically, what's happening is at the last level, you're going to have a reward, which is d to the minus h over 2 or 0. There's two cases. Okay, so it's a super tiny, and obviously you can't tell the difference between them. Okay, and the next level, so you're estimating something that's super tiny. Okay, so you got the states here, you're estimating it's super tiny, And then there's a reward here, which is value is going to be root d times as big as the value of these guys, because your weight vector can be like the all ones vector. Okay, so somehow, because basically you can show by linearity, you got a standard basis E1 to ED, you get all of them like not very accurate. Okay, but then there's one guy that's going to have like root d. I mean, this is again the LSPE. Well, this is the truth. Like this guy has value, which is root d times each of these guys' values. Okay, and the point now is you can't estimate this guy's value, so you lose here. And then you can kind of nest this. But the key in this construction is somehow you can do this in a way that you get no information about the system aside from the last level, where there's basically an exponentially small gap. So somehow you miss the gap, and the process keeps amplifying the high reward signal. It keeps kind of moving to this high reward state. So I think with that, just look at this picture, but it really sharply shows like what goes wrong with LSPE. But I felt like that construction, I was like, oh my God, like it just shed a lot of light of how we're seeing this amplification in every upper bound analysis we try. But it is pretty simple, but it's basically just that, with a couple of bells and whistles.
Thank you.
Yeah, hi. I had a query with respect to the assumption 2. If you can go back to the slide.
Yeah, sure.
Here, here we have the 1 by d. That's the identity. Do we use the minimum eigenvalues here to satisfy our expectation? Because this, because this condition phi s comma a less than 1 should be.
So for all SA, we're assuming this.
Yeah.
So this is the largest possible minimal eigenvalue you can have.
Okay.
Basically, I just want something that's like well conditioned, and this is the best possible condition. I'm just saying the condition number is D, and that's the best possible you can have in D dimensions.
Okay.
So it's for a lower bound, but yeah.
Mm-hmm.
Like you would hope that you're Pauli in the condition number, but we just set it up to be like the best possible conditioning.
Okay. Thanks.
Yeah.
So, hey, Sham, I have a question. I wonder if you have any like perspective on this. There's a setting where like all your features live in a convex hull and your data distribution is on the vertices of the hull. So now I think you can't have error amplification.
Yes.
Because you do like, it's like a L1 geometry instead of L2 geometry, right?
Yeah. Yes.
So I'm wondering if you have any like perspective or like, I don't know, like conceptual points about this.
Like the usual perspective is the favorite inequality, Cauchy-Schwarz holder. Like basically, as far as I can, like all of these things, you're just going to Cauchy-Schwarz it differently for what's going on here. So.
But I'm thinking maybe more about like practical considerations. Like, what if I create features in such a way that this is the case? Maybe it becomes much harder to satisfy realizability, but I like avoid this error amplification.
My concern, so Rusang and I have been like thinking about practice and what's going on. The main concern, so my intuition for like features on the simplex, this concern, this is not, like I would be much more impressed if you could do it with like an L2 norm rather than because basically you have no capacity on the simplex. So, and if you're really relying on like the weights being bounded in one norm in some sense, which is what's going to be the case, it's effectively just saying you can use one of those features. Like if you could do two, then I would be impressed here, and that's not going to happen here. So there's a very real sense in which that constraint in practice is it's very limiting, I think, and like we can't kind of make it like a simplex into when you scale things correctly, we can't kind of slightly increase the size of that simplex, and that's the part I'm concerned about. So kind of be much more motivated with the stuff that you're trying to do, like actually try to get features which are robust to these kind of amplification effects. But more broadly, the intuition is, yeah, it's like just stare at this equation and it's a product of matrices, but it becomes increasingly clear there are cases that aren't complete, or like Rusang was just running these experiments for a while, and like, yeah, that you don't get completeness, or you don't get the shift condition, but you don't get amplification, but it's very brittle to get it as well. So, so this question of like how to get those features, yeah, I think this is a great question, but it does feel like it has something to do with the interaction of the P matrix and the phi. Yeah, and that's the thing that we just don't really know how to deal. Aside from the stuff you were talking about, it was the only kind of case where we actually learned something, learned those features.
Follow up. Can we have a sort of OLS here with respect to the least square policy iterations, and how can we compare that to this?
How can you compare what? OLS?
Yeah. OLS or the least square policy iterations.
Oh, sorry,
yeah.
maybe I'm not. So I'm not sure if I'm totally understand the question. So this is basically OLS, okay? And policy iteration, we're going to a harder question now of actually trying to improve things, right? And that's why I think it's helpful to separate those two things apart. So like Nan's work and Chaubar's earlier work gives conditions when policy improvement will work, but sort of riffing on what Nan says, if we can't evaluate a single one of them, we're doomed. So you could think of like the sharp way of doing this. I think I'm getting at your question would be to try to figure out how accurate each policy is being estimated before you do the update. But the concern is like, if your features aren't good, you're just gonna get burned immediately, and you're back to like low distribution shift.
Yeah. So totally agree. Yeah. Thanks.
Follow up on my, since Sham mentioned experiments, I think I just want to have one small request for experiments. So besides LSTE, I really want to see how LSTD, which is this classical moment matching based methods, work in all these different settings. I think my prediction, what?
There's no difference, like.
No, there will be, no, I think their behavior will be very different. I mean, in any case, I want to see those.
We're doing a longer empirical study, so we'll ping you on that. So the reason is that you're just doing an L2 constraint on the W's. And the point is, see, every time you're doing the constraint, there's a matrix between how you're getting these things constrained. So Nan, that's exactly the same issue here. So, like I think one difference would be that one won't explode because it clips out of bounds. But my claim is the first order effect in these are entirely the same because locally that is the first order effect. You're just clipping things when it gets out of bounds. But they're like, the issue is like nearly identical is my claim. But we're definitely doing like a larger empirical set of things, but there's no difference here. Just Taylor's theorem, what you're doing, and you'll see it's kind of the same effect. But we'll definitely follow up for experiments because, I think this is also related to Akshay, is like, what the heck is happening in practice? Because we were doing random constructions and we were just like laughing because all our guesses, were like wrong half the time, right? It was like, but it's very brittle, like to say the least, is my take. But then there's a question of like, in these like big neural networks, what's happening too, which is another set of experiments we're thinking about.
Yeah, I'll stop here, but let me just mention that, like there are many I mean, recently, I think not only my lab, but also Chang Liu's lab from UT Austin, they've also developed this method like kernel loss and kernel Bellman statistics. And if you look at their entire theory, they only assume Q-pi realizability. Okay, and then they give you like, as I said, they give you intervals for off-policy evaluation. And I think their paper has a lot of like, has quite many like empirical studies across all the standard benchmarks. So I think it may be useful to also compare, and they have neural nets and so on and so forth.
Yeah,
it may be useful to look at their work.
We'll definitely take a look. I mean, the interval is like, they're going to have the same property by Taylor's theorem. And I think the point I'm making is that, your intervals are correct under realizability. See now, like the difference is we're not saying the intervals aren't correct, and that's where we agree here. It's just that realizability will not get you the right answer. Now, some cases it might, and the whole point of like my is a generic point, which I'm not going to say it always explodes, is trying to like, I think there's too much of saying because we can get an interval, it works. Like it will not always work. And now it's an empirical question of getting a handle which cases are bad and which cases are good. And putting the interval down isn't telling us that answer. Okay, and I think that's the distinction I'm making here. We might not agree whether or not it works or not, but the point is like, it definitely can amplify, and the intervals isn't gonna like address that issue. It's just gonna check it. Oh, I mean, stop sharing.
Maybe getting like more philosophical with this. I don't know, but so it, the way I would have some years ago thought about features in RL is like, okay, I'm modeling the value function well, but it does seem quite strongly from two papers you have here, and also from all our proofs failing kind of before that, that's not how we should think about maybe what these are modeling. At the same time, like a linear MDP kind of model feels too, or I don't know, if the actual dynamics are somehow linear in some basis, that feels too strong. It's like I do feel like the features should reflect the objective. I'm wondering how you are thinking about this. Like, what do we want from features?
Yeah, I mean, like, look, this is the thing that actually I was talking about Rusang is like the philosophical point is a good one. Like, and I think this is related to the policy gradient stuff that we've both been working on. That which is why I kind of mentioned this point in practice. Like in practice in the sciences, we tend not to build models. Like we really trust regression because it tends to work well. It gives us, confidence intervals, and there's all kinds of problems with model misspecification. So the more we can try to not rely on model try to be robust to model misspecification, this is needed. So that's my intuition of why we want the Q's to be linear, not the model, is because it's just hard to get models correct. Like even in H=1, it's very hard to get our actual models to be correct as opposed to supervised learning. And the unfortunate thing here is, at least for the offline setting and things in RL, like we kind of need model-ish things to be correct. And that's kind of the hard part here. And my concern is like in the offline setting, it's much harder. So in the offline setting, look, at the end of the day, if you can do a causal experiment, you want to do causal experiments. And this is clear from working lots of companies, and it's, but there is a question of like, in these scarce things, we want to squeeze as much out of the data as we can. So, so I don't like, what we want out of the features, I honestly don't know, because at least when we've tried things on some like deep learning-ish things, like you really can get amplification effects. And so I'm not, so I'm not like totally sure. Like if our goal is to get features for offline learning, that might be a very different goal than say solving like Montezuma's revenge, because it's possible you can get, our preliminary results suggest like, yeah, you might be able to get very unstable features, but it's good enough for like some incremental procedure. Okay, but whereas the features you need here, you might need further stability properties. But on the other hand, this is like, a bit warming in that, like, we're making these strong assumptions for a reason, and pointing out like Chaba's paper, a recent one. Like, this paper is awesome. Like, Chaba's here. I promised you a beer if I believe the paper. I owe you a beer, Chaba. Like, that paper for linear Q star, I think also is showing that we need much stronger assumptions. I mean, it's a much more complicated lower bound, but I think the eluder stuff and like what Akshay was saying, the Bellman rank stuff, that's kind of the closest in between, but it's far from complete what we know.